Hey, let's say we have these two state, plus state and zero state with 50-50 probability, and we want to differentiate these two states. Now, we all know that they are used in quantum key distribution protocol like B84 or B92, and the main thing is we cannot differentiate them because they are not orthogonal to each other, so there is no observable where they are the eigenbasis. Now, the question is, can we like do better than just guessing? So let's get into it. So let's say we have the state one. Can you get any hit if you have the state zero? Of course not. You if you have the state zero, you will never measure the state one. But if you have the state plus, then you can measure the state one. Now the problem is when we try. Let's say we're trying to measure the z. So now the issue is if we get the state one, then you definitely know this is plus state. But if you get the state zero, then it can be zero, it can be plus. You don't know. The same problem is if we measure the x and you get the state minus, then obviously you know that hey, this is the state zero. But if you don't get the state minus, if you just get the state plus, then it can be plus and zero. So you don't know. So how can you actually like solve this? So of course we cannot use the projective measurement. This is obvious, and but we cannot give up. So we must come up with a better solution. And the solution is, hey, we can. So the case one where we can allow the inconclusive outcome. So what we can do is define this. Let's say this is alpha 1 1 and this is alpha minus minus. Now you can say that hey, if we get the result 2 here, okay? If we get result E2, then this is definitely uh, the zero state. If we get the result E1, then this is definitely the plus state. Now to complete a POVM element, we need another element, which is E3, and E3 is basically identity minus the E1 and E2, because the sum must be identity. Now the thing is, this E3, this is the inconclusive outcome, and we of course want to minimize the probability of getting 3. So what is the probability of getting 3? Okay, so the this is basically 1 minus our probability of not getting the probability of success, you can say. And what is the probability of success? So the probability of success is, let's say we are getting the E1 and we have the I mean we are getting E1, and in case of E1 the state is obviously the plus state, and we can also get the result E2, and here the state is obviously the zero state. And if we try to calculate that, then obviously this becomes the probability of getting plus, which is half, and then there is the probability of getting E1 given this is plus, and then we have basically the half, and we can already see that there will be a there the alpha will be common here, right? Because if we take the alpha common and there are some other terms, and so we can see that hey, we need to increase alpha so that this probability is decreased, right? So how can we actually do that? The answer is we can. Okay, um, and uh, so the first condition is the E3, it has to be a positive semi-definite, and obviously we know that hey, the more the alpha, the better the probability of success here. So now what's the matrix of the E3? So we can take 1 0 0 1 minus since this is the 1 1. So this is 0 0 0 alpha, and then there is alpha, and we know that here we have something like this 1 1, minus 1, minus 1, and 1. So you can just take the matrix of E3, and since this is a positive semi-definite, we have the determinant, and the determinant must be greater than 0, and also the trace. Why? Because the determinant is the multiplication of their values, and the trace is the sum of their eigenvalues. So yeah, if you try to solve that, then you will find that hey, the value of alpha is basically 1. Okay, so just perfect. So we now have a this is how we actually get the value of the alpha max, and that's how the optimal POVM, where we can try to differentiate these two states with allowed inconclusive outcome. The POVMs can be found just putting this value of alpha. Now, there is another case when you can say that, hey, I think I can afford some error, but what I cannot afford is I have to increase the probability of detection. So now what you're trying to do is that let's say you have the state plus 0 state here, and you have the state plus here. Okay. And you are basically trying to build, let's say this. Okay, so you're trying to make some PVM element or the projective measurement, so that let's say this is the minus, okay, and this is the plus. So if you get this state, then you know that this is plus state, and if you get this state below, then you know that this is the 0 state. Now, can we do that? So let's start with the thing that let's say the projection operator here is pi plus, and here it is called pi minus. So what is the success here? Okay, so this is the case two. Okay, so where we are allowing some error, and but we know that hey, we can afford the error, but obviously we want to uh, increase the rate of success here. So this is our goal. Now the probability of success here is, of course, when you have the plus state with the probability half, then you want it to collapse in this ion, uh, in this projective space, right? So that's why you basically have this, and when you have this one, so this is basically 0 pi minus 0. Now you know that the pi plus and the pi minus, since they're basically defining the basis, they must be the identity. This is the completeness relation. Now, if you basically try to put the complete relationship here, then what you get? You get is like half plus pi plus plus then 0, 0. Sorry, there is half here as well. So yeah, sorry about that. So 0 0, and then minus 0, pi plus, then this is again the uh, 0. Uh, okay, now what we have here is this is 1, so this is half, and we can write the pi plus as the lambda plus, right? And now if you actually put this and rearrange this, you can actually, for this one, half, and then there is half, and then you can actually write these ones as um, yeah, sorry, trace of pi plus, and there is this term. Okay, yeah. Now the thing is, basically, we have this. Okay. Now, if we look at this, you can immediately say this is Hermitian because you just take the Hermitian conjugate and you can see it itself, and also the trace. Uh, sorry. So this is Hermitian, and also the trace is zero. Why? Because the outer products become the inner products, and these are just one minus one is zero. So the trace is zero. And you can also like take another thing, like let's say there is a vector uh, phi, which is let's say orthogonal to both, so zero and let's say the state plus. Okay, let's say it's orthogonal to both, and you can easily show that the psi is zero as well. So that means okay, uh, the D have since the place is zero, what and this is Hermitian, so all the eigenvalues are positive. So you can have and you can see that zero and plus they're like the plane where you have the state zero and the plus. They actually this is two-dimensional plane, so you can have either like two eigen vectors or eigenvalue where which is non-zero, or you can have all the zero eigenvalues. And if you have all the zero eigenvalues, then D must be zero, but we know that D cannot be zero here because how we have defined it, it cannot be zero. So of course we have the eigenvalue of plus C and minus C, and you can actually calculate them, and you can see that hey, the D have the eigenvalues one plus minus one by root two here. Okay, okay, so we have found that okay, we can try to make so we are trying to choose the uh, phi plus in a way sorry the pi plus in a way so that this part you can say this is already 50%, okay, and this is the additional probability we are having, and we are trying to choose pi plus in a way so that the whole thing is maximized. Now we can see that the this is basically is nothing but this one, right? Now, of course, when this is maximized, you already know that when the lambda plus is the maximum uh, value eigenvector of the uh, operator D. So what happens is if we allow that, hey, this is the eigen value of D because like D plus, this is basically the this is the eigenvector of D. So we will get this one. Okay. Then this is the maximum, and otherwise you can choose other lambda, but they will not be maximum because you can always express them with the eigenvectors of D, and you can easily show that. The maximum value you can get when it is the maximum eigenvalue eigenvectors. So yeah, when we get this one, so we have perfectly uh, calculated them. So what is the summary? So what the summary is, if we want to distinguish the state zero, the plus and zero, what you need to do is just measure this observable. Okay, so you can measure you can try to measure this observable. If you get the positive eigenvalue, which is the 1 by root 2, so then you know that you have the plus state, and you have the negative eigenvalue, then you know that you have the state zero. And now the question is like, well, what's the probability of getting this? So I will I actually already have written the probability here. Can simply try to put it here, and half plus half, and you can easily actually count that since uh, this is basically this, and you already see that you're getting here, so you will just get one by root two here, and so what is the probability here? So this is just 0.85, and there is like 4 or something. So almost 85.4%. And what was in this case? So yeah, you can also calculate the P3 here, and you can actually see that, hey, the P3, you can actually say the P3 is just one, I mean, the probability that you cannot actually distinguish the stage. This is just 1 by root 2 here. So, and we already know that 1 by root 2 is almost like 70%. So, so this is like 70.7%. So this is the probability that you cannot uh, have a conclusive outcome. So, and if you just subtract it from 100%, then you have the probability of 29 point something that, hey, we can, uh, we have either plus or zero. So, yeah, that's it. So, I hope you enjoyed the video. Thank you.